All right, in this video, I want to do another expected value problem, but we're going to do it from a money perspective. So the way that this is going to work is we're going to have a card game where what we're going to do is we're going to pick one card from a standard deck, and if the card is red, if the card is a face card, or if the card is an ace, we win $3. Face cards, by the way, by that I mean Jack, Queen, or King. And so if it's red, a face card, or an ace, we win $3. If it's none of those things, we lose $4. And then we want to know what is our expected profit, what are our expected winnings. And we'll let capital X be the random variable. That'll denote the random variable that'll count our winnings or losses. And so we're going to have two options only. We can either win this game or lose this game. And either we win $3 or we lose $4. And so what's going to happen here is we need to figure out what is the probability that we win versus the probability that we lose. And so let's calculate first what's the probability that we select a red card or a face card or an ace. And so I think the easiest way to do this is, rather than think about complements and inclusion, exclusion, let's just count. How many cards are there that are red or face cards or aces? And we just have to make sure that we're not double counting. So there's 26 red cards. There's 12 face cards, but we've already counted half of those. So there's 6 non-red face cards. So that would be the Jack, Queen, King of clubs and spades. So there's 6 of those. And likewise, there's 2 black aces. There's the ace of clubs and the ace of spades. And so altogether, this is going to be 26 plus 6 is 32, plus 2 is 34. And the size of our sample space, there's 52 cards. So altogether, the probability that we'll win will be 17 over 26. And then without doing any extra work, we know that 1 minus that value, so 1 minus this value, is going to go in the other spot. And 1 minus that value is going to be 9 over 26. Okay, so again, this value here is 1 minus 17 over 26, because I know that the sum of all the probabilities in that column have to add up to 1. And so now what we can do is compute the expected value. And the expected value of this game is going to be 3 times 17 over 26 plus negative 4 times 9 over 26. And so that's going to work out to be, let's see, 51 over 26 minus 36 over 26. And so that's going to turn out to be 15 over 26 dollars. So it's important to remember that this is dollars. So 15 over 26 dollars. So dollars. Okay. And so what this says is that notice that it's never possible to win 15/26 of a dollar. It's not even a fraction that you could get with pennies. But what this says is that if we were to play this game 1,000,000 times, so if we were to play this game a bunch of times, on average, we would win 15 out of $26. So we would win whatever that value is. It's something like 60 cents. It's more or less 60 cents. So on average, we would win 60 cents. What that says is that if we were to play this game 1,000,000 times, we would be up $600,000 roughly. So we would make $600,000 more than we lost. So our profit would be $600,000. This tells us having a positive expected value tells us that we should play this game as much as possible. So as frequently as possible, because on average, we're going to win. If we play this game lots and lots of times, on average, we're going to win money. If we had a negative expected value, that would mean that it's a bad idea to play this game over and over and over, because on average, you're just going to lose that money. And then to have an expected value of 0 is what's called a fair game. That means that the game is not tilted in favor of either the person playing the game or the person hosting the game long term. So long term, people can be up or down. It's probably going to fluctuate. And so that's called a fair game. It's when the expected value is 0. Okay.